we've seen that regular languages can be defined by finite automata. A different way to define regular languages is by using grammars. Grammars are rewrite rules that operate on words directly. A grammar defines a language. Grammars have various application areas. They are used in natural language, artificial intelligence, and to define the syntax of programming languages. And the latter kind of grammars, that's what we are interested in this course. This is an example grammar. A grammar defines rules. It tells us what we are allowed to replace by what. In this angular bracket here, we have variables. So sentence is a variable, article is a variable, noun is a variable, and verb is a variable. And these arrows, they are used to define rules, production rules. And these rules say that we're allowed to replace certain things by other things. We are allowed to replace the variable sentence by the word consisting of variables article, noun, verb, article, noun. We are allowed to replace article by the, or using another rule, we are allowed to replace article by a. We are allowed to replace noun by farmer, or using another rule, we can replace noun by cow. And we can replace verb by milks. So using these grammar rules, we can construct a sentence. So we start with a certain start variable, in this case sentence, and then we start applying these rules and we derive something using these rules. Let's have a look how this works. We now want to use the grammar in order to derive this sentence. The farmer milks a cow. So we start with the start variable sentence and we apply our grammar rules. Currently there's only one rule that we can apply here. The first rule, so we replace sentence by article, noun, verb, article, noun. That's our first production step. Now we can continue replacing. We can now replace any of these variables. To keep it simple, we will replace the variables from left to right. So I will start with article. And we have two options. We can replace article by the or by a. Since we want to derive this sentence, we will replace it by the. Now we pick this variable noun. We have two options again. We can replace it by farmer or by cow. If we want to get this sentence, we replace it by farmer. This verb, we have only one option. We replace it by milks. The article, we have two options. We can replace by the or by a. If we want this sentence, we replace it by a. And finally, we replace this noun. We have two options, by farmer or cow. If we want this sentence, we pick cow. So from our starting variable sentence, we have derived the farmer milks a cow. So formally this is again a word. It does not contain any variables anymore. So it's a terminal word. It's a sentence or a word in the language generated by this grammar. And clearly we had different choices. We could also derive other sentences. So we could also derive a cow milks a cow, for instance. Formally, a grammar G consists of 4 ingredients. We have a finite set V of non-terminal symbols. They are also called variables. In the example that we've looked at, the variables were written in these angular brackets. So sentence, article, noun, verb were variables. We have a finite set T of terminal symbols. In the example, these were the, a, farmer, cow, milks. And here it's not so crucial that you consider the entire word as a terminal. You could also think of the terminal just being the letters from the English alphabet. Then, for instance, the word the would be composed of 3 terminal letters. We have a starting symbol or start variable S, and we have a finite set of production rules that are written in the form x arrow y, where x and y are words consisting of variables and terminals. The left-hand side must be non-empty, and it must contain at least one symbol from the variables. Now, most of the grammars that we will look at in this course will be of a simpler form, where the left-hand side consists of a single variable. These grammars have a special name. They are called context-free grammars. So a grammar is called context-free if for every production rule, the left-hand side is a variable. And this is the kind of grammars that we will work mostly with in this course. Also, the example that we have seen was of this form. The left-hand side was always a single variable. One of the very well-known applications of grammars is the Backus-Naur form. The Backus-Naur form is often used to define the syntax of programming languages. The Backus-Naur form is a set of production rules, and the variables here are indicated in these angular brackets. The left-hand side of each rule is just a variable, so the Backus-Naur form is nothing else than a context-free grammar. In the example, we've already seen how a grammar can be used to derive words in the language. Now, a single derivation step is formally defined as follows. If we have a production rule x arrow y, then we get derivation steps of this form. We replace x by y inside an arbitrary context. That means we can have an arbitrary word u left of x, this is preserved, and an arbitrary word v right of x, and also this context is preserved. We just replace the inner part, the x, by y, and the uv context stays the same. Let's have a look at an example. Here we have a grammar with variables just s, terminal letters a, b, start variable s, and we have 2 production rules. S can be replaced by a as b, or s can be replaced by lambda. Now what can we derive? We start with our starting variable s. Now the shortest word that we can derive is by applying this rule. We immediately go to lambda. So we get the derivation step, which is denoted by this fat arrow from s to lambda. But we have more options, of course. We can also start with s, and we can apply this rule. Then we get a derivation step from s to a as b, and now we can continue deriving from this word because we still have a variable that we can replace. Now we replace the variable s inside the context, left context a, right context b. And if we want to get the shortest word possible from here, we can apply the rule that replaces s by lambda. So s gets replaced by lambda, ab gets preserved. We get just the word ab. But we can of course also apply the first rule multiple times. We can go from s to a as b, and we can again apply this rule. Then the s is again replaced by a as b. We get aa s bb, and now we could, for instance, apply the second rule. The s becomes lambda. We get aa bb. And of course, we can derive longer rules. We can apply the first rule n times, and then we would get, I think it's easy to guess, we get a to the n, b to the n. Now, this is a single derivation step, but we also would like to denote that we have longer derivations. And longer derivations we denote by this fat arrow with a star. So this is a derivation. Formally, this is the reflexive transitive closure of the single derivation step. You can imagine this derivation just as saying that we have a derivation of 0 or more single derivation steps. So it can be an arbitrary number. It could be an empty derivation of 0 steps, or 1 step, 2 steps, or any higher number of steps. So in this example, we have a derivation from S to lambda, we have a derivation from S to AB, we also have a derivation from S to AABB, and so on. Grammars define languages. The language generated by a grammar G, denoted by L of G, consists of all the terminal words that can be derived from the starting variable. So we do not take everything that can be derived from the start variable, but only those words that do not contain any variables. Only the terminal words are in the language. So let's have a look at an example. This is the grammar that we've seen on the last slide. We have our production rule S goes to ASB, and we have a second production rule S goes to lambda. Now, we have already discussed what terminal words we can derive. We can derive lambda. If we apply the first rule once and then the second rule, we get AB. If we apply the first rule twice and then the second rule, we get AABB. So in general, if we apply the first rule n times, we get A to the n, B to the n. And if you recall what we've learned about regular languages, then you know that A to the n, B to the n is not a regular language. So this grammar here does not give rise to a regular language. In order to make defining grammars more convenient, we introduce a few notational conventions. Roughly speaking, we want to denote grammars simply by writing the production rules. We do not want to explicitly say what are the variables and what are the terminals. And in order to do so, we use the following convention. We will always denote variables by uppercase letters and terminals by lowercase letters. In this way, from the production rules, it's immediately clear what are the variables and what are the terminals. For instance, in this example grammar, we have variables S and A, capital A, and we have terminals lowercase a and lowercase b. Moreover, to help us write grammars, we use the following notational convention. We write, instead of n rules with the same left-hand side v and right-hand sides w1 up to wn, we write just something that looks like one rule, but it's short for n rules, with 1 times the left-hand side v, and on the right-hand side we separate the different possible right-hand sides that we can rewrite to using such a vertical bar. So if you look at this example, then you see here that we have A can be rewritten to lowercase a, capital A, lowercase b, or, and this is formally a second rule, A can be rewritten to lambda. So this abbreviates 2 rules with the left-hand side A. If we do not specify what's the starting variable of such a grammar, then implicitly the starting variable is S. And if we want to deviate from this, then we have to explicitly say what our starting variable is. Now let's have a look at these 2 grammars. What is the language generated by the first grammar? So we start with the starting variable S. We can replace S by capital A, lowercase b. Okay, so we have 1b and we have a variable a in front. A can be replaced by lowercase a, capital A, lowercase b, or by lambda. So we've seen this before. If we apply this multiple times, we basically get a to the n, b to the n, and we finish with lambda. But we have already 1 additional b, so we have a to the n, b to the n, plus 1 additional b at the end. So we get a to the n, b to the n plus 1. What does the second grammar give us? The second grammar, if we apply the first rule n times, we get a to the n, b to the n, and in the middle an s. If we apply the second rule, we get 1 additional b in the middle, but since this additional b is at the start of a string of b's, so we just have a to the n, b to the n plus 1 again. So both of these grammars generate the same language, a to the n, b to the n, for n greater or equal 0. So let's practice a bit with grammars. In this exercise, we are asked to give a grammar for this language. Let's maybe recall what the ingredients of this language are. We have here a set AB, so that's just a finite language containing the words AB, to the power of star, so that's the Kleene star, meaning that we take all the words that we can build from the basic building blocks AB. So this is just all the words over the alphabet AB, including the empty word. Then a C follows, and after the C we get an arbitrary word over the alphabet BC. So there's many possible grammars for this language. So if you try to solve this and you come up with a different solution than I'm showing on the slide, then that's perfectly fine. It's just one of the solutions that is possible I will suggest on the slides. So what's the idea of the solution that I use here? We start with a starting variable s, and we say that s rewrites to x, c, y. So x and y are variables again. And as you can guess, this c is the c here. And we will use the x to generate an arbitrary word over ab, and we will use the y to generate an arbitrary word over bc. How can we use x to generate an arbitrary word over AB? Very simple. We need basically 3 rules. We say that x can rewrite to ax, generates a a, or to bx, generates a b, or it can rewrite to lambda. Using these 3 rules, we can from x derive arbitrary words over AB. And similarly, we add 3 rules for y to generate an arbitrary word over bc. Y can rewrite to by, to cy, or to lambda. So we have a grammar consisting of 7 rules, and the language generated by this grammar is precisely this language. But again, there's many possible solutions, and it does not mean that this is the only possible solution that I've presented here. So you can very well come up with a different solution that is still correct for this exercise. A word is called a palindrome if the word is equal to its own reverse. So the word reads the same whether we read it from left to right or from right to left. An example of such a palindrome is the word Hannah. Whether we read it from left to right, it's exactly the same as if we read it from right to left. Now, in this exercise, we are asked to construct a grammar that generates all the palindromes over the alphabet AB. So we want the language of all words over AB such that the word is a palindrome. So we want to have a grammar that generates words that read the same if you read them from the left or from the right. So the idea is simple, namely we generate at the same time the letter on the left and on the right, and we enforce them to be the same. So we make a rule, S can rewrite to ASA. Applying this rule will create an A at the front of the word and an A at the end of the word. And we want to be able to do the same with B, so we also generate BSB. Now what can we do with this rule, or with these 2 rules? From S we can derive ASA. If we apply the first rule again, we get AAS, AA. And if we apply the second rule, then we get AAB, S, B, AA. So this already looks very much like a palindrome, but it's not yet the terminal word because we still have this variable S in the middle. So at the moment, the language of this grammar is still empty because we cannot derive any terminal word. we need at least one rule that can rewrite to lambda. And here lambda is not a terminal word consisting of L, A, M, and so on. It is just the empty word. So now we can derive the word AA, B, B, AA. So this is already a nice palindrome. So with this grammar now, we can derive any palindrome of even length. And the even length is enforced because we always generate a letter on the front and the end at the same time. So we always generate two letters at the same time. So all the words that we can derive here are of even length. But of course we also have palindromes of odd length. We also would like to, for instance, be able to derive just the letter A. This is a palindrome. If you read it from the left or from the right, it's the same, but it has odd length, and it's not in the language of this grammar yet. So what we need is, we also need to be able to just produce A or just produce B. Now, is this sufficient? Indeed, this is sufficient because now we can put a letter A or a letter B in the middle at the end. So for instance, if we take this derivation and we do not replace the S by lambda, but we could replace the S by an A, let's say, we would get AA, BA, B, AA. So any palindrome of odd length has either an A or B in the middle, and using this rule S goes to A or S goes to B, we can put exactly this A or B in the middle. So this grammar indeed generates all palindromes of even or odd length, so all of them over the alphabet AB. In the second part of the exercise, we are asked to give a grammar for the complement of the language that we have just considered. So we are asked to give a grammar for the complement of the language of all palindromes. So these are all the words over AB that are not palindromes. So let's see how we do that. So how do we define a grammar that generates all the words over AB that are not palindromes? The crucial point is that if we want to enforce that we do not have a palindrome, we have to make sure that there is some index I, such that the ith letter when we look from the left is different from the ith letter when we look from the right. So we start by producing the same number of letters left and right. So we don't care about what letters, but we make sure it's the same number. So we say that X is an arbitrary letter. It can rewrite either to A or to B. So our variable X stands for an arbitrary letter A or B. So now this rule generates arbitrary letters in the front and in the back of the word. It just makes sure it's the same number. Now we want to enforce that there is a mistake. So some letter that is different if you look from the left than if you look from the right. So for instance, we can say that from the left we want to see an A, but from the right a B. Now this makes sure that we don't have a palindrome, because it's an A if you look from the left, it's a B if you look from the right. So it cannot be a palindrome. And the A, B are embedded in the same number of letters from left and right. Now we need one more rule, because it could also be a B in front and A in the back. And this already looks quite nice. So now we have two rules that allow us to introduce a mistake which makes the word not a palindrome. But now we cannot finish simply by saying that S can rewrite to lambda, because if we allow S to rewrite to lambda, then we are not sure that this rule, which introduces the mistake, actually has been applied. So we somehow have to make sure that these rules that introduce the mistakes are actually used. So we switch from S to T. Basically, the switch from S to T says that, okay, we have introduced a mistake. So T indicates the word cannot be a palindrome. So now, if the word is not a palindrome, so it looks different from the outside, looking from left or from right, then what we produce in the middle here, the T, can be anything. It doesn't matter anymore. We have already ensured that there is a mistake. So if the t can be anything, we can just say t can be either xt, so an arbitrary letter followed by t, or lambda. So let's have a look at some example derivation. Let's say what would we like to derive. Let's say we have a word that starts with AA, ends with AA, maybe also has a B, and maybe here's a B, there's an A, and in the middle we have BA, something like this. So how would we derive this? We derive this basically from outside in. Outside we have two A's, so we would get X. And this we can do in 2 steps. Okay, so now we have derived the outside A. We can continue. We do it again. We again do 2 steps. Okay, now we've derived these 2 outside A's in the front and in the back. Now we are going to derive the B. So we again use the rule A. Okay, now we have derived the AAB from the front and AAB from the back side. And now is where our mistake comes in, namely we have a B if we look from the left, and we have an A if we look from the right. So we are going to use now a rule that introduces a mistake, namely this rule. So we get A, B, B, T, A, B, A, A. Okay, so now we have introduced this B and this A, and what is left to be done is we have to derive this middle part, BA, and from T we can derive an arbitrary middle part. So we can derive A. We want first a B, so we go to xt. We derive the x to a B. And now we want to have an A, so we apply the rule once more. And now we replace the t by lambda, and we are done. So if I take this word and replace the t by lambda, then hopefully we have exactly the word that we were intending to derive. Okay, so indeed, using this grammar, we can derive any non-palindrome over the alphabet AB. We've seen that grammars can generate languages that are not regular. We've seen a grammar that generates a language A to the N, B to the N, which we know is not regular. Also, the language of palindromes on the last slide is also not a regular language. So the question is, how do we ensure that a grammar generates a regular language? So we will see that there is a syntactic restriction on the shape of the grammars that ensures that we get precisely the regular languages. A grammar is called right linear if all of the production rules are of one of the following forms. First of all, the left-hand side of every production rule must be a variable. Second, the right-hand side of the production rules must be of the form either UB, where U is a terminal word of any length, and B is a variable, or just a terminal word of any length. So the word U does not contain any variables. So therefore this rule is called linear because there's at most one variable in the right-hand side. And it's called right linear because if there is a variable in the right-hand side, then it appears at the right end of the right hand side. Moreover, such a system is called strictly right linear if the terminal word always has length at most 1. So if the terminal word u is always either the empty word or a single letter. Now let's look at an exercise. Let's try to give a right linear grammar for this language. So this language consists of words that start with an arbitrary word over AB, followed by 2 consecutive letters A, followed by an arbitrary word over B, so just an arbitrary number of B's. So we are looking for a right linear grammar for this language. Now, since our grammar is right linear, we cannot make the grammar of the following form. I mean, if we would try to do this, where x is responsible for generating an arbitrary word over AB, and y is responsible for generating an arbitrary word over B, then this might be a nice grammar, but it's not a right linear one. It's not of the shape required by right linear grammars, where the variable, there can only be one variable in the right, and only at the right end of the right hand side. So we have to do it differently. We somehow have to generate the words in this language from left to right. So how do we do this? First, we have to generate arbitrary words over AB. Simple enough. We can generate an A, or we generate a B, or we say that we are done and we switch to the next part, namely generating the AA. How would we do this? We could, for instance, say that once we are done with generating an arbitrary word over AB, we go to a new letter T, and we can say that T now is responsible for generating this inner part. So T can generate the AA, and then we again, because we can generate the AA only once, we have to again switch to a new part that now is responsible for generating the B's. So let's say that T generates AA and switches to U, and now U is responsible for generating an arbitrary number of B's. So we say that can generate 1B or lambda. Now let's have a look. So indeed, starting from S, we can generate arbitrary number of A's and B's in any order. And if we are done, we switch to T. So indeed, that part generates an arbitrary word over AB. T will generate AA. And then we switch to U. U generates an arbitrary amount of B's and finishes with lambda. So indeed, this grammar generates precisely this language. And of course, we could optimize a bit. So strictly speaking, we would not need the variable T, because T has only a single production rule and it immediately switches further to the next letter. So we could immediately say that from S we go to AAU, and then U generates an arbitrary number of B's. So this would also be a possible solution for grammar that generates this language. So this grammar that we have here is indeed right linear. On the left hand side we always have a single variable, and on the right hand side we always have a terminal word followed by a variable, terminal word followed by a variable, terminal word followed by a single variable, terminal word followed by a single variable, or just a terminal word. In the second exercise, we are asked to give a right linear grammar for this language. So the words in this language start with AB always, and then they are followed by an arbitrary number of times a word from this language. So you have here this clean star, meaning an arbitrary number of times words from this language. What's in this language, the words start with an arbitrary number of A's followed by CB. And once this part is finished, the word ends with a B. So again, we are asked to give a right linear grammar for this language. We want to have a right linear grammar, so that means we have to generate the words in this language from left to right. Every word starts with AB, So from the starting variable s, we can immediately generate ab, and we switch to a new variable t. And now this new variable t is responsible for generating words in this language. Now, how do the words in this language look like? Again, we have to generate them from left to right. So we have to first generate an arbitrary amount of words in this language. And once we are done with this, we finish with B. So how do we generate now an arbitrary amount of words in this language? So we have to decide whether we want to generate, because here's a star, this could be 0 copies. So we have to decide, do we want to generate one more copy, or do we want to finish with B? So we can say that one clause should be we want to generate more copies. Let's say that we switch to a variable u, which then is responsible to generate a word from this language, or we finish with B. So now our variable u is responsible for generating at least one word from this inner language, from this language, and once it's done, switch back to t. So u now generates an arbitrary number of a's followed by cb. How do we do this? We generate an a followed by u, and once we are done, we finish with cb and we switch back to t. Okay, so what do we have now? So from S we generate AB, we switch to T. T can either switch to U, meaning that we produce at least one instance of these words, or we say that we want 0 instances, then we switch immediately to B. U will now generate one instance of a word in this language. It's an arbitrary number of a's, followed by cb, then we are done, and we switch back to t because we might want to generate either more instances of these words in this language, or we want to finish with b. So this grammar indeed generates all the words in this language. And this grammar is also right linear. For every rule, we have that the left-hand side is variable, and the right-hand side always consists of a terminal word followed by a single variable. Here an empty terminal word followed by a single variable, just a terminal word followed by a single variable, or terminal word followed by a single variable. So this is a right linear grammar for this language. Next, we will see that every right linear grammar can be transformed into a strictly right linear grammar that generates the same language. So we can always make sure that the terminal word u here has at most length 1, so it's either a single letter or the empty word. This is this theorem. It says that for every right linear grammar G, there exists a strictly right linear grammar that generates the same language. The idea of the construction is very simple. We start with an arbitrary right linear grammar G, and now we transform it into a strictly right linear one by splitting rules that are not strictly right linear. So if we have a rule that is not strictly right linear, so where this terminal word u here has length greater than 1, so is longer than a single letter, then we are going to split this rule into 2, such that u becomes shorter. So I'm putting the b, this variable, in brackets here, because in our right linear grammar, the production rules can or cannot have a variable. So if I put this in brackets, it means it can be there, but it does not need to be there. And it's to be understood that in the sequel, if I put this in brackets again, it means that the b should be there if it's present here. So if our word u has length greater than 1, it means that it's of such a form. So u must be of the form aw, where a is a single terminal letter, and w is some word that is still non-empty, so still consists of at least one letter. Now we introduce a fresh variable x, so x is not among the variables that already are in the grammar, must be fresh, and we split the original rule as follows. Instead of this original rule, we have now two rules. One rule that says a can be rewritten to lowercase ax, that's producing this first letter of u, and then x, this fresh variable, has a rule that allows to rewrite to wb, where the b is here if and only if the b is present in the original rule. So if you combine these two rules, then from a we get ax, and from x we get w possibly with a b, and this gives us exactly, because aw is equal to u, as we have assumed, this gives us exactly the original rule. From a we can derive ub. Now it's just derived in two steps instead of a single step as we had before. So what does this help? We can still derive the same words, and now in two steps. The crucial part is that this rule now is strictly right linear, because we have a single letter followed by a variable. And this rule, the w, might not yet be strictly right linear, but the w is at least one letter shorter than u. So possibly we have to keep splitting, but eventually w will get shorter and shorter, and if we have split every rule that is not strictly right linear, if we continue this, at some point we will have a grammar that is strictly right linear. So each time we split, w gets one letter shorter, so at some point it will have length at most 1, and then our grammar is strictly right linear. We are given a right linear grammar, and we want to make this grammar strictly right linear. So we apply what we've just learned. We are going to split the rules. This rule is not strictly right linear. The word u, the terminal word in front, has length more than once. So we have to split this rule. We introduce a fresh variable, let's say x, and we introduce a fresh rule, x rewrites to bcs. Now if we apply the rule s goes to ax, followed by the rule x goes to bcs, then we get exactly the original rule, namely that from s we can derive abcs. Now this rule is still not strictly right linear, so we have to split again. We introduce a fresh variable, and we say that this fresh variable y rewrites to cs. Now from s we can derive ax, so from s we can derive ax. From this we can derive aby. From aby we can derive abcs. So now in 3 steps we have derived the original rule. Okay, we are almost done. This rule is still not strictly right linear, so we also need to split this. Let's introduce a fresh variable z, and we say z goes to b. Now all of our rules are strictly right linear, and the grammar generates the same language as the grammar that we have started from. So we will see now that right linear grammars give rise to precisely the regular languages. So let's take the non-deterministic automaton given on this slide, and let's try to make an equivalent right linear grammar. So a grammar that generates the language accepted by this automaton. So how do we translate a finite automaton into a grammar? The crucial idea is to consider the states of the automaton as variables in our grammar. So Q0, Q1 and Q2 are now variables in our grammar, and I will write them with capital letter to make clear that we are speaking about variables. So our starting variable is Q0, because Q0 is the starting state of our automaton. So Q0 can produce an A and switch to Q1. Q1 can produce a B and switch to Q0. Q1 can also switch to Q2 while not producing anything. Q2 can produce a C and remain in Q2. So now we have translated the 4 transitions of our automaton into 4 grammar rules. But we are not yet done, because from the starting variable Q0, we can still not derive any terminal word. Every word that we derive still has a variable in it. So how do we get to terminal words? We have to somehow be able to say that the word can get accepted if we are in a final state. So our final states are Q1 and Q2. So how do we express that Q1 and Q2 are accepting? We can express this in a grammar by saying that they don't need to produce anything, they don't need to switch. They can simply accept, so rewrite to lambda. So Q1 can rewrite to lambda, and Q2 can rewrite to lambda as well, because Q2 can also accept. So now we have a grammar that generates precisely those words accepted by the automaton. So now let's take some word as example. Let's take, for example, what word could be generated by the automaton. We could have A, B, A, C, A, B, A, C, A, B, A, C. Now, how would we derive the word A, B, A, C in our grammar? We start with Q0. From Q0, we derive A, Q1, A, Q1. Then from Q1, we will derive B, Q0. So we get A, B, Q0. Then we derive again A, Q1. So we have A, B, A, Q1. Then we take this lambda transition, which corresponds to the rule where Q1 can be rewritten to Q2 without producing anything. So we have A, B, A, Q2. From Q2, we derive C and we remain in Q2. That corresponds to this rule. Q2 rewrites to C, Q2. So we have A, B, A, C, Q2. And now finally, Q2 can accept. So we have a rule Q2 rewrites to lambda, and we get A, B, A, C derived by our grammar. The exercise that we've just done, the translation of a non-deterministic finite automaton into a right linear grammar, works also in general. So we have the following theorem. For every non-deterministic finite automaton M, there exists a right linear grammar G, such that the grammar generates the same language as the language accepted by the automaton. Now, the proof of this fact is just as the exercise. We start with a non-deterministic finite automaton. We know already that every non-deterministic finite automaton can be translated into one that accepts the same language and has a single starting state. So we assume that our non-deterministic finite automaton has a single starting state. And now we are transforming this automaton into a grammar. The variables of the grammar are the states of the automaton. The terminal letters are just the input alphabet of the automaton, and the starting variable of our grammar is the starting state of the automaton. Now we translate the transitions of the automaton into grammar rules, and the transitions are translated as follows. We have a production rule from Q to alpha Q prime if we have a transition from Q to Q prime with label alpha in the automaton. So formally this means that Q prime is in delta Q alpha, where delta is the transition function of the automaton. And here alpha can be either a letter from the input alphabet or lambda for a lambda transition. Moreover, we have production rules Q can rewrite to lambda for every final state Q of the automaton. Because we somehow have to be able to say that we accept the word. In the grammar, this means that we have to erase the variables and produce a terminal word. So we have to be able to erase the last variable, and we rewrite to lambda. Then we have the following, namely that in the grammar, we have a derivation from a variable a to a terminal word u followed by b, if and only if in the automaton we have a path labeled with u from state A to state B. And from this property, which we can prove by induction on the length of the word u, we can derive that the language generated by the grammar is just the same as the language accepted by the automaton. So we've just seen that non-deterministic finite automata can be translated into right linear grammars. So right linear grammars are at least as strong as non-deterministic finite automata. But the reverse translation is also possible. So for every right linear grammar, we can transform it into a non-deterministic finite automaton that accepts the language that is generated by the grammar. So how do we prove that? We start from a right linear grammar G, and as a first step, we make this grammar strictly right linear. Recall that making a grammar strictly right linear was by splitting the rules. So we split the rules until the terminal words u in the right hand side have at most length 1. So that means that these terminal words u are either terminal letters or lambda. And now if we have a strictly right linear grammar where all the rules are of this form, we translate it into a non-deterministic automaton as follows. We define a non-deterministic automaton that has as input alphabet the terminal letters of our grammar. As set of states, it has the variables plus one fresh state omega, and this fresh state is used for acceptance. So it's the only accepting the only final state of our automaton. Now, how do we translate the production rules into transitions of the automaton? We do this as follows. So the transition function is given by the following transitions. We have a transition from A to B with label u if in the grammar we have a production rule A rewrites to ub. So u here can be either lambda, then we have a lambda transition, or it's a single letter, then we have a normal transition for an alphabet letter. And additionally, we have some transitions to our new final state omega. So we have a transition from A with label u to omega if in the grammar we have a rule A rewrites to u without a variable. So the idea is that we can think of the rules that have a variable as switching the state of the automaton, whereas the rules that do not have a variable, it means that we erase the variables, we are ready with producing our terminal word. So this corresponds in the automata to accepting the word. Recall that we are speaking about right linear grammars. So a linear grammar has at most a single variable in the right hand side. That means if we start deriving words, each word that we derive only has a single variable. And if we are using right linear grammars, then the single variable is at the right end of the word that we have derived. So that means if we erase this variable, then we are done. We have produced the word and we can no longer rewrite. And again, this corresponds in the automaton to accepting, so we switch to the state omega, and omega is our final state, the word is accepted. Now you can establish the following property, namely you can show that from the starting variable in our grammar, we can derive a word W that only consists of terminal letters if and only if the automaton that we have defined accepts the word W, and that means that the language of the grammar, the language generated by the grammar, is just the same as the language accepted by the automaton. As an exercise, we are asked to translate this right linear grammar into a non-deterministic finite automaton. So we are asked to translate this right linear grammar into a non-deterministic finite automaton. The first step of this translation is to make this right linear grammar strictly right linear. So we have to split this rule. We introduce a fresh variable, let's call it u, and we say that u rewrites to this. Now this is still not strictly right linear, we need still one more split. Let's call the variable v, and v rewrites to this. Okay. Now we have a strictly right linear grammar, and we can translate this into an automaton. The states of our automaton are basically the variables of the grammar, plus an additional state for acceptance, omega. So we have a state S, we have a state T, we have a state U, and we have a state V. And additionally, we need the state omega for acceptance. Let's put this here. Omega. So omega is our final state for acceptance, and S is the starting symbol of the variable, so the initial state, the starting state of our automaton. Now, from S, we can go to T by producing A. So we have an A transition from S to T. We produce an A. From T, we can switch to U via A. So we have a transition from T to U with label A. From T, we can also just produce a B and erase the variable. So that means that the production of our terminal word is finished. In the automaton, this means that we are going to accept the word. So we have a transition from T to our accepting state omega with label B. From U, we can switch to V by B. So from U, there's a transition to V with label B. And from V, we have a transition with label C to our starting state S. We have a transition from here to here. Let's bend this a bit with label C. So this is our automaton that corresponds to this strictly right linear grammar. This automaton accepts precisely the same language as the grammar generates. On the last slides, we've seen that non-deterministic finite automata can be translated into right linear grammars. That means every language that can be defined by a non-deterministic finite automaton can also be defined by a right linear grammar. We've also seen that right linear grammars can be translated into non-deterministic finite automata. So also, every language that can be defined by a right linear grammar can be defined by a non-deterministic finite automaton. And if you put both together, it means that they are equivalent in the sense that the class of languages that is defined by non-deterministic finite automata and by right linear grammars is the same. They both give rise to the class of regular languages. So we may conclude that a language L is regular if and only if there exists a right linear grammar that generates the language. So this is interesting because we have now already seen 3 different ways to define the class of regular languages. Regular languages can be defined by deterministic finite automata, by non-deterministic finite automata, and now we know that they can also be defined by right linear grammars. Each of these is equivalent in the sense that we can translate between them. Every deterministic automaton is also a non-deterministic one. We can translate non-deterministic finite automata into deterministic ones. We can translate non-deterministic finite automata into right linear grammars and back. So we can translate between each of these concepts. They are all equivalent. They all give rise to the same class of regular languages. So we have seen that right linear grammars give rise to regular languages. But what about left linear grammars? Left linear grammars are defined in a way very similar to right linear ones. The only difference is highlighted in red here. The variable in the right-hand side of the production rules is now not at the right end of the right-hand side, but at the left end of the right-hand side. So, in some sense, our right linear grammars are producing the words in the language from left to right, whereas the left linear grammars produce the words from right to left. So, a grammar is called left linear if all of its production rules are of one of these forms. That means the left-hand side again must be a single variable, and the right-hand side is a variable followed by a terminal word or just a terminal word. Now, what's the difference in the power of left linear and right linear grammars? And it turns out that there is no difference in power. They both give rise to the same class of languages, namely the class of regular languages. A language is regular if and only if there's a left linear grammar that generates the language. So also left linear grammars give rise to the regular languages, just as deterministic automata, non-deterministic automata, and right linear grammars. How do we prove that? We have the following, namely we know that a language is regular if and only if the reverse of the language is regular. If you recall, we have proven that using non-deterministic automata by turning around the arrows in the transition graph and swapping the final and starting states. Now, the reverse of L being regular is equivalent to saying that there is a right linear grammar for the reverse language, just because we know that the right linear grammars define precisely the class of regular languages. So if this language is regular, there must be a right linear grammar for it. And now if we have a right linear grammar for the reverse language, then if we reverse the production rules, that does not mean we swap the left and the right. What I mean by reverse the production rules is that we reverse the left-hand side and we reverse the right-hand side of the production rule. Now, the left-hand side is a single variable. If you reverse this, nothing changes. But if we reverse the right-hand side, then the variable that is here on the left will get to the right of the right-hand side. So by reversing the right-hand side of all production rules, we turn a right linear grammar into a left linear grammar. And now it's not hard to see that if you reverse the right-hand side of all production rules, then from a grammar for the reverse language, you obtain a grammar for the non-reverse language. So we obtain a left linear grammar for the original language L. So we have a chain of deductions. This is always if and only if. And we have concluded that a language L is regular if and only if there's a left linear grammar for the language L. Now we conclude the subject of regular grammars with a note of caution. Namely, we have learned that right linear grammars give rise to regular languages and left linear grammars also give rise to regular languages. But if we mix right linear rules and left linear rules in the same grammar, then we can get out of the class of regular languages. So here we have an example grammar. The first rule is right linear, the second is left linear, and the third is both left and right linear. So we are mixing left and right linear rules. And as a result, the language of this grammar, the language generated by the grammar, is no longer regular. The language generated by this grammar is a to the n, b to the n. So this shows that if we mix left and right linear rules in the same grammar, we no longer get regular languages. So the result holds only for purely left linear and purely right linear grammars.